Section 5.3 is about complex rational expressions, and what those are is that they're like conventional rational expressions, except that instead of having a polynomial divided by a polynomial, that you can have rational expressions in the numerators and denominators. And they look kind of intimidating. If I scroll down to get one, like even this one, like number 2, like that looks pretty intense compared to what we've had before. And it is harder. There's more to do. But when I've done 091 before, this has always been a section that's kind of a sticking point, where it tends to be one where I think it's easy to make this harder than it is. And I mean, certainly subconsciously, right? Nobody's going to pick that. Nobody's going to say, I wish this was harder. I'm going to go ahead and make it harder. But just because of what they look like, I think that's really easy to do subconsciously. And they do look more difficult. There's a lot more going on. And the other part of it is like having the different methods, because there are two different ways that you can simplify them. I'm never going to mandate that you have to do it the first way or you have to do it the second way. As long as you have kind of a familiarity with both of them, then whichever one looks like it's going to be easier or feels like it's going to be more comfortable, just do that one. And I think that'll help a little bit. So, all right. So I said already that it's like a complex rational expression. It's like a rational expression, except that you can have rational expressions in the numerators and denominators rather than just polynomials. All right. So if I go back down to where we were, so looking at number 2, if you look at that thing, that's got 3 rational expressions in it because it's got the x over x minus 2, and it's got the 1 over x squared minus 4 both in the numerator, and then it's got a 1 over x plus 2 in the denominator, right? So there are rational expressions that show up with it. And that's what these generally are like. And so there are 2 ways to simplify them. One way, which right now is probably going to feel like it's a little more straightforward because it turns the problem into something we were doing relatively recently, is this first one where if you simplify the numerator and denominator individually. Basically what you do there is you rewrite the numerator and denominator by themselves so that they're each just conventional rational expressions. And whatever you have to do, you get a common denominator, add, subtract, whatever. Then what you would end up with if you did that is that you'd have a rational expression divided by another rational expression, which sounds like a thing that we just did in section 5.1. Where then if you divide one rational expression by another, you can essentially get to the same place by multiplying by the reciprocal. And you would do that, you cancel out whatever you can cancel out, simplify it. Then that way I think right now would probably feel a little bit more straightforward. But the other way to do it sometimes is actually faster. And it kind of looks at because there's less wording. So this thing about getting the least common denominator. And really, I guess that would be the overall least common denominator. So whatever rational expressions you've got within your complex rational expression, you get the least common denominator of all of those denominators. Then you multiply the top and bottom by whatever that is, by that overall least common denominator. Then you'll probably have to use a distributive property, but you'll be able to cancel a bunch of stuff out. And then what you'll end up with is just a rational expression. So rather than ending up with one rational expression divided by another, you get to the end part maybe a little bit faster. I guess it depends on how complicated your overall least common denominator is. Right? If that's something that's really insane, then maybe the simplification takes forever and you don't actually get there faster. So it depends. But I guess, sometimes it's the first one that's faster, sometimes it's the second one. But usually they're about the same. So let's see what we can do. So this I already kind of mentioned. I'm never going to mandate this, so if the homework tells you to do it, don't worry about it. So if there's a homework problem that says use method 1, like it explicitly says use method 1, but you would rather use method 2, go ahead and use method 2, that's fine. They'll get you to the same place. So for this section, whichever method you want to use, just use that one. I don't have the administrator privileges to go in and change the wording on the homework. So if there's a question where I like the way it works out, but the phrasing kind of specifies a certain method to use, just ignore the method that's being specified. Certainly you could use that method if you wanted to, but you could also use the other one. All right. Now this first example, because this one is somewhat short, I figured this would be a good one where we could kind of have a comparison with both methods. So for this one, we're going to simplify the numerator and denominator individually first, because that's method 1. So for the numerator, if we're going to add 1/5 and 1 over x together, we're going to need a common denominator. So the least common denominator of 5 and x, well, that's just going to be 5x. Right? They don't have any common factors. So then what we're going to end up with is that we're going to have 1/5 times x over x, and I usually change the color here. So I'll go back and do that and make this, I think maroon is usually the LCD color. So like so, right? Because we want a 5x, we've got the 5, but we need the x. And then multiplying by x over x effectively is like multiplying by 1, but we're just doing it away so we get what we want in the denominator. And then we're going to have plus 1 over x, which needs to be multiplied by 5 over 5, because in this one we've got the x, but we don't have the 5. So we multiply by 5 over 5. Then what we're going to end up with is x over 5x from the first product plus 5 over 5x from the second. So that's x plus 5 over 5x. And then what about the denominator? Well, the denominator here, we don't actually have to do anything because that's already a rational expression, right? It's not like the numerator where that was the sum of two rational expressions. The denominator is already there. So the denominator, at least in this one, we're all set. So this is already a rational expression. All right, so then what can we do as far as rewriting that? So, all right, I guess we know that we can rewrite the numerator. So I guess I'll just rewrite the whole thing first, and then we'll go from there. So 1/5 plus 1 over x plus 5 over 2. That's what we started with. But we know we can rewrite the numerator as x plus 5 over 5x because we already got that common denominator and combined the expressions together. And then we'll have x plus 5 over 2 on the bottom. And so then this is one rational expression divided by another. I usually write the division horizontally instead of vertically. So I can rewrite it real quick, just maybe to make the multiplication by a reciprocal a little bit more explicit in the next step. Maybe this would help with that a little bit. So just writing the division horizontally, but then that would be the same as multiplying by the reciprocal. So we could rewrite this as x plus 5 over 5x times 2 over x plus 5. And then from here you can see what's going to happen. We're going to be able to cancel things out. So I'm just going to rewrite that so I have one that I can kind of draw on. So x plus 5 over 5x times 2 over x plus 5. And then we can cancel the x plus 5s. So that's what I'm going to do. And what we're going to be left with is 2 over 5x, right? 1 times 2 over 5x times 1. So 2 over 5x. And that is going to be the answer. So that's one way of handling that one. The other way, which, let's see, I guess I'm writing kind of close to 1b, so I'm going to draw on a black line as kind of a barrier. All right, so what we can do if we're going to use the other method is that you look at the individual denominators that show up. So we have 5x and 2. So what we're looking for, if we're going to use that overall LCD, so the LCD of 5x and 2, well, those don't have any common factors, so you just have to multiply them all together and you get 10x. So what that means is that you would multiply the numerator and the denominator by 10x. All right, so then what I'm going to do is I can rewrite this as, so it's 1/5 plus 1 over x over x plus 5 over 2. And we're going to multiply by 10x over 10x. Perhaps it would be easier to see this way, because I think maybe things would line up a little better with all these rational expressions. You could write 10x over 10x as 10x over 1 divided by another 10x over 1. That might help a little bit just for alignment purposes. If you don't need to have the ones in there, if 10x over 10x and then just distributing the 10x through the numerator, if that's enough, then I guess you don't have to write in those denominators. But I'm going to write it like that. So then what we're going to have, and I think I like this in the front. So I'm going to rewrite the order since we're multiplying. So 10x over 1 times 1/5 plus 1 over x over 10x over 1 times x plus 5 over 2. Okay, so let's see what we're going to get. We're going to end up with, well, I guess it'll have 10x times 1/5. So that'll be 10x over 5. And then plus 10x over x. And then in the denominator, we're going to have 10x times x plus 5 over 2. I'm not going to distribute the 10x through there because if there's anything that we can cancel, it would actually be easier if it was already factored. And right now it's already factored. But in the numerator, 10x over 5 is just going to be 2x, right? Since 10 divided by 5 is 2. So you'd have 2x, and then 10x over x is 10, right? So you have 2x plus 10 on top. And then what can we do with the bottom? Well, 2 goes into 10 5 times. We could do that. So there is some cancellation here. So 2 goes into 10 5 times. So then that means that we could rewrite the denominator as 5x times the quantity x plus 5. And the bottom's factored, but now the top isn't, because 2x plus 10 is a common factor of 2. So if you factor out that 2, you'd have 2 times x plus 5 over 5x times x plus 5. And pretty clearly we got a common factor of x plus 5 between the numerator and denominator. So we could cancel those out, and that's exactly what we're going to do. So cancel them out or divide them out, whichever phrasing you want to use there, and we're going to get 2 over 5x. And that's the exact same thing that we got in 1a. So both methods are going to work. Here they're about the same length, and usually that's what happens. Once in a while you'll get one that's shorter than the other, but I guess we can just kind of, at least for this video, go back and forth, just so that way at least both methods show up multiple times. I think that's probably the best thing for me to do with this video. All right, so let's see. Number 2, maybe number 2 would be easier just to do it the second way, but I'm going to do this one the first way, and then do 3 the second way, because 2 and 3 are actually pretty similar to each other. So here, 2 with the numerator. We need the least common multiple of x minus 2 and x squared minus 4, right? So our LCD would be equal to the least common multiple of x minus 2, and if you factor x squared minus 4, that factors into x plus 2 times x minus 2, right? So then our least common denominator is going to be that. It's x plus 2 times x minus 2. All right, so then what we're going to do is we're going to have x over x minus 2 times, since we're missing an x plus 2 for the common denominator, so we're going to need that. We're going to multiply by x plus 2 over x plus 2. The other one we're going to leave alone because we already have x plus 2 times x minus 2. So for the other one, we're just going to say, all right, well, then that's plus 1 over x plus 2 times x minus 2. Let's see. So what we're going to get, if we multiply x by x plus 2, that's going to be, well, I mean, I guess I can just write it like this first. So x times x plus 2. And it might be easier just to use the x squared minus 4 for now, since we're going to have to rewrite this a whole bunch of times. We can always refactor it later if we need it. So like that, and then distribute the x, and I guess we can also combine terms. So what we're going to end up with is x squared plus 2x from that first numerator. The second numerator is going to give us a 1, and then this is over x squared minus 4. All right, so pretty clearly we can factor both of those, right? The denominator is a difference of squares. The numerator is a perfect square trinomial, but we'll deal with that in a little bit. Then the denominator, so there, the least common denominator would be the least common multiple, I guess really of 1 and x plus 2, which is really just x plus 2. Right? So all we're really going to have to do with that denominator is multiply x by x plus 2 over x plus 2, and we should be good to go. So I guess I'll write it as x over 1 just to get the numerators and denominators to line up a little bit better. And then we're going to multiply by x plus 2 over x plus 2. And then the 1 over x plus 2 already has the common denominator, so we can just leave it alone. Let's see, and then we're going to end up with, let's see, we'll have x times x plus 2 over x plus 2 plus 1 over x plus 2. And then if I distribute the x in that first numerator and combine the numerators together, we're going to get x squared plus 2x plus 1 over x plus 2. All right. So let's see, we've got all of that stuff taken care of now, since we have the numerator and denominator both written as rational expressions. So then, let's see, I guess I can write it down here, that what we're going to end up with is going to be, let's see, it would be x squared plus 2x plus 1 over x squared minus 4 for the new numerator, and then over what we got for the denominator, which is x squared plus 2x plus 1 over x plus 2. All right, well, I prefer division written horizontally instead of vertically. So all I'm going to do is rewrite it, and then I'm going to rephrase this as multiplication by the reciprocal. All right, so now x squared plus 2x plus 1 over x squared minus 4 times x plus 2 over x squared plus 2x plus 1. All right, well, I guess you could write the x squared plus 2x plus 1s as x plus 1 quantity squareds. That's not really going to help because you can just cancel them now anyway. But I'm going to write this, I guess, maybe as just one giant rational expression this time. But I'm going to leave the x squared plus 2x plus 1 as it is. But then the x squared minus 4, it would help if we had that factored. So x plus 2 times x minus 2 times x squared plus 2x plus 1. And then it looks like we should be able to cancel a whole bunch of stuff. Right? I mean, I guess you could do it all at once, or you could do it like piece by piece. Might as well do it all at once, I guess. Make it faster. So x squared plus 2x plus 1, that's a factor of the numerator and denominator. So is x plus 2. So we're not really going to be left with all that much. We're going to be left with a 1 on top and an x minus 2 on the bottom. And that is the answer. So a surprisingly simple looking answer considering what the problem looked like at the beginning, but that's sometimes how these go. So that's what we ended up with there. All right, next, number 3, a similar idea, right? And looking at these, you can see the perfect, well, not the perfect square, the difference of squares, and you can see the factors of the difference of squares in there. So, all right, well, we'll do this one the other way. We'll do it where we get the overall least common denominator, and we'll go from there. So, the overall least common denominator, if we're going to use the second method, that's going to be the least common multiple of z minus 3, and z squared minus 9, which is really z plus 3 times z minus 3 when it's factored. So then what's that going to be? Well, you need a z in that least common multiple. You would need a z minus 3, and then you'd need a z plus 3, because that shows up in the z squared minus 9. So what we're going to do then is we're going to multiply the numerator and denominator by z times z minus 3 times z plus 3. Okay, so that's what we're going to do here. All right, so we've got 1 over z plus 4 over z minus 3 over z squared minus 9 plus 1 over z minus 3. And I hope with this one that my z's and my 2's don't look exactly like each other. Like in that z squared, it almost looks like it's the same character. I don't know that I can help that too much, especially with a square, to try to make the floppy 2, at least with a tablet. It's kind of tough. All right, but then we're going to multiply by the overall least common denominator on the top and on the bottom. So let's see, I guess we'll do it as times z minus 3 times z plus 3 over 1 over z times z minus 3 times z plus 3 over 1. Okay, so I guess we got to use the distributive property in both cases. So let's see, this expression is going to get pretty wide in the next step. So, all right, let's see, we're going to have, if I distribute the thing in maroon, like just on the top, since we have 2 terms in the original numerator, and we're going to multiply both of them by this thing. So I'd have 1 over z times z times z minus 3 times z plus 3 over 1, then plus 4 over z minus 3 times z minus 3 z plus 3 over 1, and then this is going to be all over. We're going to do the same thing down here. So z over z squared minus 9 times z plus 3. And actually, it's the other way around, right? It should be a minus then a plus. Not that it matters. So I fixed the second one on the fly. Now I just have to go back and fix the first one. There we go. And then, let's see, that's over 1 plus 1 over z minus 3 times z minus 3 times z plus 3 over 1. Okay, let's see. You could start canceling things now, which might actually be the way to make this shorter. But I'm going to write it where it's cleaned up a little bit and then just cancel a bunch of stuff in this next step. Let's see, and I want that equal sign actually a little bit lower, I think. There we are. All right, so we're going to have z times z plus 3 times z minus 3. I know I just switched the order. I can't help it. I like to do the plus first. Over z, and then plus 4z times z minus 3 times z plus 3 over z minus 3. And then on the bottom, let's see, z squared, since that's what z times z would be, times z minus 3 times z plus 3 over, if you want to factor the z squared minus 9, you could write that as z plus 3 times z minus 3. Alternately, since we're about to cancel that, if you could see it as just, oh, there's the z squared minus 9 and there its factors, I can cancel that and I can cancel the factors, that's fine. That's totally legitimate. But I kind of wanted to make it look sort of explicit in here. So z times z minus 3, z plus 3, and then this is over z minus 3. And we should be able to cancel a ton of stuff out. So let's see what we got. The first one, the upper left, we can cancel out z's. Next one, we can cancel out z minus 3's. In the lower left, we can do a whole bunch because we can get the z plus 3's and the z minus 3's. And then the lower right, we can get the z minus 3's. So notice when I do the cancellation, in each of those 4 rational expressions, now I got a 1 on the bottom. That's what happens when you use the overall least common denominator. Because then this will turn into just one rational expression over the other. And let's see exactly what that will look like. I guess before simplifying anything else yet, you would have z plus 3 times z minus 3 from that first one. Then from the second one, you'd have 4z times z plus 3. On the bottom, you'd have a z squared from the first one, and then plus z times z plus 3 for the second. And then those can all be simplified. So in the upper left, you've got conjugates, so that's going to be the difference of 2 squareds. So z squared minus 9 if you multiply that out. Then toward the right, if you distribute the 4z, you'd get 4z squared plus 12z. Then on the bottom, z squared, can't really do anything with that, but then if you distribute the z through the z plus 3, you get z squared plus 3z. All right, if we combine like terms, we're going to get 5z squared plus 12z minus 9 over 2z squared plus 3z. Let's see, then the bottom clearly factors, right? You could factor out a z. So you do that, you're left with z times 2z plus 3. And then does the top factor? Well, I guess you could think about it as though you're going to do the rainbow method, because that's the check. If the rainbow method can be done, then it can be factored. Either way, either that way or the other way where maybe you'd have to do a little bit of trial and error. So let's see, if you're going to use the rainbow method, you need a pair of factors of negative 45 to add up to 12. That exists. Positive 15, negative 3. So since that exists, this is factorable. So we need a 5z and a z to get the 5z squared, right? Since 5 is a prime number. Let's see, it looks like it's going to be this. Looks like it's plus 3 there, minus 3 there, to give us that right middle term of plus 12. And that's the answer, because nothing here cancels out. So this is actually the final answer to this one. So 5z minus 3 times z plus 3 over z times 2z plus 3, with all the pieces factored. I mean, I guess 5z squared plus 12z minus 9 over 2z squared plus 3z is also kind of just as well, because we couldn't factor anything out. But with this one, we did it the other way, right? If I scroll back up a little bit, we got the overall least common denominator. And when you multiply the top and bottom by that and then distribute it to the individual rational expressions, you will get a bunch of cancellation, and eventually you end up with just one polynomial divided by the other. So you just get a single rational expression. And then you just have to check, see if you can simplify it any further. So there's the other method with that one. Then let's see, number 4. I guess number 4 could be done either way. In a way, it looks like number 4 is going to be something weird, because there's no rational expression in the denominator is just a polynomial. Well, I mean, that would mean that if you were going to do it with the first method, you just wouldn't do anything to it, right? It's fine the way it is, right? You don't need to get a common denominator. And I guess maybe that's the way to go. So if we were going to do this with the first method, then for the numerator, those two denominators have no common factor. So the least common denominator would just be x minus 2 times x minus 1. So then we'd have x over 5, or x plus 5, rather, over x minus 2. We're missing the x minus 1 to get the common denominator, so we'd have to multiply by x minus 1 over x minus 1. Then minus x plus 3 over x minus 1. And here we're missing the x minus 2. So times x minus 2 over x minus 2. All right. Then it looks like what we're going to have to do is FOIL a little bit, because we're going to have x plus 5 times x minus 1 over x minus 2 times x minus 1, then minus x plus 3 times x minus 2 over x minus 2 times x minus 1. And then, let's see, foiling that first numerator, that's x squared plus 4x minus 5. So we'll have that over x minus 2 times x minus 1. I'm going to leave the x minus 2 times x minus 1 as it is, just in the off chance that when we combine terms very shortly, that we'd be able to actually cancel something. I guess we're going to find out. But we FOIL that second numerator, that's going to be x squared plus x minus 6 over x minus 2 times x minus 1. Then if we're going to combine the numerators together, we're subtracting, so just be careful. Make sure you subtract the whole numerator rather than just the first term, right? Make sure you get all the signs right. So we'll have x squared plus 4x minus 5, and then minus the whole other numerator. So I'm going to put it in parentheses, x squared plus x minus 6, and then this is going to be over x minus 2 times x minus 1. All right, so distributing the minus, we're going to have x squared plus 4x minus 5, and then minus x squared minus x plus 6, right? Minus negative 6 will be plus 6. And then dividing by x minus 2 times x minus 1. All right, so then if we simplify that, we're going to end up with, let's see, 4x minus x is 3x. Looks like 3x plus 1 over x minus 2 times x minus 1. So that's our numerator. And then the denominator is fine. So we don't have a ton of space left, but that's actually going to be okay. Because what we can do here is then we can say that that's going to be, let's see, well, it'll be 3x plus 1 over x minus 2 times x minus 1 divided by 3x plus 1, right? So I guess I can section off this numerator here. But then we can rewrite this as multiplication by the reciprocal. So 3x plus 1 over x minus 2 times x minus 1 times 1 over 3x plus 1, right? Reciprocal of 3x plus 1 would be 1 over 3x plus 1. But then you'd be able to cancel out the 3x plus 1s. So we can do that. And so then that means that we're going to have 1 over x minus 2 times x minus 1. And that is going to be our answer. All right. So not too bad, right? And not too bad because the denominator really didn't have a whole lot to do, right? So that helped. No question that helped. Number 5, it doesn't have a ton of space here. It's really small, but it looks weird when there's only one rational expression within the complex rational expression. Like it almost looks like a trick. It's not. There are 2 ways that you could do this one, just like usual. I guess either you could just get the common denominator on the bottom, or you could say that the overall least common denominator is just x plus 2, right? So I think that's what I would do. I would do it this one the second way and just say that the overall least common denominator is x plus 2. So I'm going to multiply the numerator and denominator by x plus 2. So then we're going to have 1 over x plus 2 plus 2, and we're going to multiply by, and this time I'm not going to use the over 1s. I'll write it the other way, where you just write it as x plus 2 over x plus 2. And then with that, in the numerator, we're just going to have 1 times x plus 2. All right, that's not anything crazy. It's just x plus 2. And then if you distribute the x plus 2 in the denominator, what you would end up with is 1 times x plus 2 over x plus 2, and then plus 2 times x plus 2. The thing that's on the left in the denominator is just a 1, right? It's x plus 2 over x plus 2. So you could say, well, then this is going to be an x plus 2 on top. And then on the bottom, you'd have 1 plus 2 times x plus 2. But then we can distribute that 2 on the bottom. So we're going to get x plus 2 over 1 plus 2x plus 4. So it looks like this is going to be x plus 2 over 2x plus 5 if you combine like terms. And there's nothing to cancel, right? 2x plus 5 doesn't factor. So there's the answer. I think there's one of those that you get in the homework in this section, 1, maybe 2, where it almost feels like you're doing something wrong because they're so short. But this one is so short just as a function of that there aren't a lot of rational expressions in the original problem, right? In the complex rational expression, there's only one of them. And that does reduce the work. If you only have one of them, you're going to do less work than if you have 3 or 4. So it feels wrong, but it's not for this one to be this short. All right. Then going on to number 6 and number 7. I think number 6 is a little more conventional. I stuck 5 in here because it was tiny, and I just needed to put it on a page where I could fit it with another one, pretty much. Oh, yeah, that's what 6 is. Okay. This looks different, but yet it's not. It looks a lot different, right? Because you go, where's all the division? It's there, it's just that this one's written differently. It's got all those negative exponents. If you wrote this thing with positive exponents, then you'd see the division. So that's what we're going to do first. We're going to rewrite this with positive exponents. So 3 times xy to the negative 1, you could write as 3 over, well, I guess 3 over xy to the first, which would be 3 over xy, right? And then minus 3 over y squared, if you rewrite that with a positive exponent. And then on the bottom, you'd have 1 over y squared minus 1 over x squared. I think this one's faster with method 2. So I would just get the overall least common denominator. So it would have to be the least common multiple of xy, y squared, and x squared. So really that's just x squared, y squared. Right? They're all monomials in those denominators. So it's just give me the biggest powers of x and y that show up someplace. Right? So biggest power of x is an x squared. Biggest power of y is a y squared. All right. Looks like we're good to go. So then we are going to multiply the numerator and denominator by x squared y squared. All right, so that's what we're going to do here. We're going to say, all right, we got 3 over, and I need that equal sign to actually be way lower. Might as well fix it now. That needs to be about there, probably. All right, so 3 over xy minus 3 over y squared over 1 over y squared minus 1 over x squared. And then we are going to multiply by x squared y squared over x squared y squared. So x squared y squared over x squared y squared. And then if we distribute the x squared y squared in the numerator and denominator, so we'd end up with 3 x squared y squared over xy minus 3 x squared y squared over y squared, right? So there I've got the x squared y squared multiplied by both of those rational expressions in the numerator. And then that'll be over x squared y squared over y squared, and then minus x squared y squared over x squared. Okay, so lots of things that we can cancel out or divide out. That first rational expression in the upper left, that one would end up being 3xy because of that law of exponents where if you're dividing you could subtract the exponents. So you have an x squared in the numerator and x to the first in the denominator, so 2 minus 1 is 1. That's why I just have an x to the first. Same thing with the y. Next rational expression, you could cancel or divide out the y squareds, and you would just have 3x squared. Then on the bottom, you could, again, cancel out the y squareds. In that first one, you're just left with x squared. And then in the second one, you can cancel out the x squareds, and you're just left with y squared. So you end up there. All right. Well then, let's see. Can we factor anything? In the top, looks like we would factor out a 3x. So if we do that, we'd be left with y minus x. And then on the bottom, that's a difference of squares, so we could factor that as x plus y times x minus y. And it looks like we can almost factor something because we have a y minus x on top and an x minus y on the bottom. So what you could do is factor a -1 out of one of those. I'm going to factor out of the top. So I'm going to say that that's 3x times -1 times -y plus x, right? Factoring out the -1 would just change all the signs around. And then I'll have x plus y times x minus y on the bottom. But -y plus x is the same thing as x minus y, right? So then I can rewrite that as 3x times -1 times x minus y over x plus y times x minus y. And those x minus y's, certainly, they're going to cancel out. So then, let's see, 3x times -1, you could just write as -3x, right? If you do the multiplication, and it would be that over x plus y. Or I guess the most conventional thing is to put that minus out front, so to have it as the negation of 3x over x plus y. But that is our final answer. Okay, so we ended up doing the same stuff, basically. I guess factoring out this -1 toward the end, that was kind of a new wrinkle. But the thing that was different about this problem, it was like the very first step, right? If I go back to where it is, it's with that original problem how we've got all those negative exponents in there, and when you rewrite that expression with all positive exponents, you get something that looks like what we've been doing, right? You get a complex rational expression with 4 individual rational expressions in there. So then it's either method 1 or method 2. I picked method 2 here because I thought that would be a little easier, but they're about the same. And yeah, it kind of turns back into what we were just doing. Let's see. Then there's a word problem, I believe, for number 7. The other thing I believe about number 7 is, believe it or not, that expression for v actually works out to be really, really simple. It does not look that way now. I'm well aware of that. But I think that's what will happen. Let's see, and that should be 2 years, not 5 years. Not that it matters. It doesn't really affect the problem. But if you want to get the accounting parts of this right, that square should match up with the number of years. All right, so let's see. What we're going to have to do first is simplify v just as a single rational expression. So the only thing that's going to be different about that, I guess, would be that you have that p out front, and that just kind of hangs out there. So that'll be there in every step. But you could either use method 1 or method 2. This is another one where, like, since the denominators are the same in those two rational expressions, I would probably just use method 2 because you'd be able to cancel out all kinds of stuff. So and we can do that, right? So for part A, what I would do is I would say that the overall least common denominator is going to be 1 plus r quantity squared. So then you're going to multiply the top and bottom by that, right? So then we're going to have that v equals p times 1 minus 1 over 1 plus r quantity squared over r over 1 plus r quantity squared. And we are going to multiply by 1 plus r quantity squared over 1 plus r quantity squared. All right. And then if we do that, then what we'd get in the numerator, so we're going to have, I guess, p times, and then we're going to have 1 times 1 plus r quantity squared minus 1 over 1 plus r quantity squared times 1 plus r quantity squared. And then denominator, where we're going to have r over 1 plus r quantity squared times 1 plus r quantity squared. An awful lot of 1 plus r quantity squareds in this, but we can cancel a bunch of them out, because what we're going to ultimately end up with here is that v is going to be p times, and then we'll have 1 plus r quantity squared, since multiplying by 1 doesn't do anything, and then minus, I guess if I multiply through, I'd have 1 plus r quantity squared over 1 plus r quantity squared, and then the denominator would be r times 1 plus r quantity squared all over 1 plus r quantity squared. And then you'd get a whole bunch of cancellation. Right, you could cancel those, you could cancel those. And so what you're going to end up with is p times, and then the numerator is going to be 1 plus r quantity squared minus 1. Right, from canceling the 1 plus r quantity squareds out. And then the denominator is just r, right? That's r times 1. Okay, well then we could square that binomial. So we could have that v is p times, and then the numerator will be 1 plus 2r plus r squared minus 1 over r. So the 1 and the minus 1 are going to add out. So this is going to be p times 2r plus r squared over r. You could factor out an r on the top. So this is p times r times 2 plus r over r. But then you could cancel those r's out, right? So ultimately, look how simple this looks at the end. Because you can cancel that r and that r, right? And then what you're going to get at the very, very end is that v is equal to p times 2 plus r. See? I said it worked out really simply. But night and day. right? What the original expression looked like was overly complex, but then when you simplify it down and write it as a single rational expression, that looks really simple. And that actually helps for part B. Because then part B, if I scroll back up to it, it says determine the value of an account paying 5% when the annual deposit is $1,000. Okay, so P, like how it says P dollars, P stands for principal, right? So it's sort of an accounting word. And then the R, I guess obviously is for rate. So I just have to convert the 5% into a decimal, and we're going to do this really fast. So for part B, the 5% would mean that R is equal to 0.05, right? To convert to decimal form, just move the decimal point 2 places to the left. And then the other thing is that P is 1,000, right? So then V, if V equals P times the quantity 2 plus R in general, then here specifically, V is going to be 1,000 times 2 plus 0.05. So then this is 1,000 times 2.05, which would be, and I guess I can stick the dollar sign in here, 2,050. That's the answer. So with the V formula being all simplified down, then when you sub values into it, it's much easier. Which totally makes sense, right? I mean, you could sub, like, if you really wanted to, like, if this seemed like it was too simple and you wanted it to be harder, then you could use the original expression for V that's up here, that's typed in there toward the beginning. You'll get the exact same answer. So if you wanted to do it that way with, like, a bunch of extra algebra, it'll still work. I'm assuming that no one really wants to pick that, though. And if you do it the simplified way, it just tumbles right out here pretty nicely. And I think that's what the word problems are like, generally, in this section. They're not all about, principles and rates and things, but it's usually a part A where you simplify and then a part B when you substitute in. And after you simplify, the substitution gets really easy. So nothing wrong with that. All right, I think that's everything for 5.3. So again, I know these look kind of crazy, and this generally is one where it is sort of a sticking point, I think, with 091. This is one where people tend to get sidetracked or tend to think like these problems just look totally insane. And they do look insane. But if you just kind of think like piece by piece, like, okay, here's the thing that looks insane, but it has a bunch of rational expressions in it. Let me just get an overall least common denominator and see what happens. Or let me just simplify the numerator and denominator and then see what happens. Right? If you just kind of look at it in individual pieces, then maybe it doesn't feel quite as crazy. So anyway, I think that's about it for section 5.3.